In this video, we're going to be talking about one of our two types of random variables, the discrete random variable. And remember, when we defined the discrete random variable, we described it as being countable or mappable to the natural numbers. So if we have a finite or countable number of potential outcomes, or even an infinite number of potential outcomes that we could potentially count, we're going to call that a discrete random variable. And for each of our different types of random variables, we have an associated probability distribution. And for the discrete random variable, this is generally given to us in the form of a table, a graph, or some type of formula. And for that distribution, we have two associated rules. The first rule is that the probability for any potential outcome, which we're going to call x, is going to be greater than or equal to 0. And our other rule is that the sum for the probabilities for each of our outcomes, so the p of x, is going to be equal to 1. And if you remember from our previous video when talking about probability rules, these are basically the exact same rules that we dealt with before, where each possible outcome has some associated probability between 0 and 1, and the sum of all those probabilities is equal to 1. So since we have our random variable and we have some associated probability distribution, we might want to figure out what the expected value or the expected outcome of that particular experiment is going to look like. And the way that we do that with a discrete random variable is with a formula. And our formula is going to be mu, which remember from before is the population mean, mu, where the sample mean was x bar. So when we're dealing with probability distributions, we're talking about the population, is equal to e, the expected value of our random variable x. So we're going to say that the mean is equal to the expected value of our random variable, which is going to be equal to the sum of our particular outcome, so x of I, times the probability of that outcome happening, so times p of x of I. And if you want to look back and compare this to what our mean formula was before, we had mu was equal to the sum of x of I over n. And these are actually equal if we consider p of x of I equal across the board. So if each potential outcome is equivalent, we would say that p of x of I is equal to 1 over the total number of outcomes we have, which would be n. So if we wanted to change this into our original formula, we would just need to have the probabilities of each of those outcomes equal to each other. So now that we have the mean of our particular distribution, we can also calculate the variance. So we're going to say sigma squared, which again, remember we're dealing with population, is equal to the expected value of each of our particular values. So we're going to say x of I, or x, minus mu, and that quantity squared. And if we're doing the expected value of it, we're going to write it like this with square brackets around our function. And if we wanted to write that out in the actual summation notation, we would say that's equal to the sum of x minus mu, that quantity squared, times the probability of that particular value happening, so times p of x. That's just going to be our formula for our variance. And if we want to refer back again to our formula from variance before, we had the sum of x minus mu, that quantity squared, all over n, because remember we're dealing with population, so it's not n minus 1, it's just n. And again, we get that same equivalence, where if p of x was equal across the board, it would be equal to 1 over n, which would turn into our formula down here. When talking about our discrete random variable and its associated probability distribution, just using these formulas and variables, it can be a little confusing. So let's walk through a simple example. So for our example, we're going to have one die, and we're going to roll it one time and look at the possible outcomes. So our outcomes are just going to be the x, which are going to have the possible outcomes of 1, 2, 3, 4, 5, and 6. So then to turn this into a probability distribution, we need to have the associated probability for each of our outcomes, which we're going to call p of x. So we're going to have a probability that each particular outcome happens, so probability that x happens, and we're going to define those for each of our different outcomes. So for the first one, we're going to say that the probability of rolling a 1 is 0.2. The probability of rolling a 2 is 0.1. 3 is 0.3. 4 is 0.05. 5 is 0.1. And 6 is 0.25. So we have our probability distribution now because we have our possible outcomes and their associated probabilities. And if we want to look at our two rules, we can see that the probability of each particular outcome happening is greater than or equal to 0, because we have all positive numbers. And the sum of all those is equal to 1. So if we wanted to walk through and add up all these together, we would get a sum of 1. Now, if we want to know what our expected outcome from our particular experiment is, we just need to walk through and calculate x times p of x for each of our possible outcomes, and then we add them all together. So we're going to say x times p of x for each of our outcomes, and we're just going to walk through and multiply those together. So we're going to get 1 times 0.2 is 0.2, 2 times 0.1 is 0.2, 3 times 0.3 is 0.9, 4 times 0.05 is 0.2, 5 times 0.1 is 0.5, and 6 times 0.25 is 1.5. So if we look at these values, we see that they no longer sum to 1. We actually add them all together, we get a value of 3.5, which means our expected outcome, or our expected value for our particular experiment is 3.5. And if you want to look at our possible outcomes, we just have our 1, 2, 3, 4, 5, and 6, which means that 3.5 isn't actually possible when rolling our die. So the easiest way to think about an expected value is that it's not really the value that you would expect to see, it's the average value that you would get if you averaged an infinite number of rolls together. So if we rolled our die, we got a particular value. We would then keep track of those values as we're going along and average them all together, and at the end, we would expect the average to equal 3.5. So now that we have the expected value for our probability distribution of 3.5, we can use that to calculate the variance for our probability distribution. And the first thing that we're going to need to calculate is we're going to need to calculate x minus mu, and that value squared for each of our possible x values. So for the first one, we have 1. So we would have 1 minus 3.5, which would be negative 2.5. And if we squared that, we would get 6.25. For 2, we would have 2 minus 3.5, which would be negative 1.5. Squared is 2.25. We would then have 3 minus 3.5, which would give us negative 0.5. And if we squared that, we would get 0.25. And if we look, our distribution is actually kind of mirrored here. So if we want to look at these values, they're just going to be repeated in opposite order, going down the other side. So we're going to get 0.25, because we have 4 minus 3.5, which is that same 0.5, which we're going to square. We would then have 2.25 and 6.25 for our other two values, because if we looked, it would be 6 minus 3.5, which would give us 2.5. We square that, we get 6.25, and so on. And then once we have these values, we need to calculate the probability of x times that value. So p of x times x minus mu squared for each of our values. So we're going to calculate that. To do that, we just multiply our values in p of x times x minus mu squared. So we get 0.2 times 6.25, which is going to give us 1.25. We have 0.1 times 2.25, which is just going to be 0.225. We have 0.3 times 0.25, which is going to be 0.075. We have 0.05 times 0.25, which is going to be 0.0125. 0.1 times 2.25 is going to be 0.225. And we have 0.25 times 6.25, which is going to be 1.5625. And then to calculate the variance, we just add up all these values together. So if we add those all up, we would get the sum of 3.35, which will be the variance for our particular distribution. So just to quickly review, we have our distribution for rolling a particular die, where we can have the possible outcomes of 1, 2, 3, 4, 5, and 6. Then to create a probability distribution, we need to have associated probabilities for each of those outcomes, which is going to be our column for p of x. So that's a probability for each of our possible outcomes. We can then get the expected value for our distribution, or the mean of our distribution, by multiplying each possible outcome times the probability of it happening and adding those values together. So x times p of x, sum all that, and we get the expected outcome for our experiment of 3.5. And then we can also calculate the variance of our experiment by taking x, or each possible outcome, minus the mean, squaring that value, and then multiplying it by the probability of it happening, and adding all those values together to get 3.35 for our variance. So again, we have mu is equal to 3.5, and sigma squared is equal to 3.35. And again, if we wanted the standard deviation, sigma, we would just take the square root of sigma squared. So sigma is equal to the square root of sigma squared, which is equal to the square root of 3.35, which is equal to 1.83. So now we have the mean for our distribution, the variance, and the standard deviation for our distribution, just based off of our distribution table, the particular outcomes, and the probability of them happening.